So
may I start?
Yes, sir. You can share your screen. In the meanwhile, I can just introduce you.
अरे ठीक है सर. Sir, is it visible?
Yes, sir. Yes, sir. Yes, sir. It is visible.
My
Sir.
screen is visible, sir.
Yes, sir. It is visible, sir. Yes, sir. So, participant, it's my pleasure to introduce Professor Biparthi, who is currently working as an associate professor at IIT Roper. He's also currently serving as the head of the School of Artificial Intelligence and Data Engineering at IIT Roper. So, prior to this position, he was an assistant professor at IIT Guwahati and MNIT Jaipur, our institute only. So, sir is currently focusing on various research areas. One of the most important area which he focuses on is computer vision only and deep learning. So, he has published several papers in reputed journals, including IEEE Transactions and all, and also peer-reviewed conferences such as WSEB, ICIP, CVPR, and so many others. So, with this, I now request Professor Santosh Viparthi, sir, please start the session.
Thank you, Deepak, for welcoming me to this particular today development program.
Thank you, sir.
To avoid this internet glitches or any other thing, so I'm trying to turn off my video. So participants, you are free to chat. If you have any questions, you can feel free to put your queries in the chat box. So I'll go to verify that regularly. Okay. Yeah. Once again, thank you, Dr. Deepak, for this particular session. So today we will going to discuss some of the concepts on basics of deep learning and the different architectures and their working principles and the limitations of the existing works. Yeah. So now, what is the main objective of developing any of the deep learning architecture? The first objective is to get the generalizability, right? So what is meant by generalization? Generalization is nothing but while you are trying to train your model, how well it is performing good in the training during the training process is not important. How well it is performing better in the during the testing time. It's nothing but whenever you are trying to test your models in the real world scenarios, if you are getting the same accuracies or the performances, whatever you got in the training process, is called generalization. So the best example of our generalization is our smartphones. In our smartphones, we have a face recognition or fingerprint recognition, right? So your smartphone, once you are going to be registered with your fingerprint, it will going to open up whenever you are only going to give your fingerprints. If let's assume if I am going to try to unlock your phone with my fingerprint, it will not going to. That means that fingerprint recognition algorithm is having a generalization capability. It is also trying to detecting authorized user and unauthorized users as well. That is what called generalizability. So as you can see that in a conventional machine learning algorithm, how we will try to do it? Y equal to f of x. Y is a function, is a f of x. So what is x here? X is some features. Depending upon what type of the data you are going to use, it with audio, text, or image, or whatever it might be. Now that input data or input features you are passing to a function called f to get the desired output called y. This is what our expectations are. How you can able to make your model to understand what are the important information or features which are presenting in the input called x. In order to make your function f to know what the features are, to do that, we are trying to dividing a raw data into two different distributions. One is a training distribution, another one is testing. That means both the training and the testing data are coming from the same data distributions. From the same data, we are dividing into two parts. One is a training set as well as a testing set. Now, as you might be already knew about the neural networks part, So let us to just take a minute to see about the neural networks part. So let's assume your input data is of 16 plus 16. If you would like to use a simple fully connected neural network, the input here is that simply flattening of the given input data. That means the two-dimensional data you are converting into one-dimensional vector form. This particular one-dimensional vector you are considering as an input vector. Now, there is a one hidden layer we have used with the 100 hidden units. The number 100 we have selected here for a easy numerical calculation, nothing else. And output neurons, because as the given input sample is belongs to the character, I have a 26 characters are there. So my output neurons are 26. So I hope this particular architecture you are very clear, right? It is a very simple and straightforward architecture. Now what we have done, the given input, the raw sample directly converted into one-dimensional vector form as an input neuron and given to the one hidden layer, and pass on to the output layer to get the desired output. This is what the simple architecture is. So how many number of parameters are involved in this process? Simple. As it is a fully connected neural network, I have 256 input neurons are there, 100 hidden units are there. So 256 into 100, 256 parameters. And as I am using the one hidden layer with the 100 units, so I can use the 100 biases. So 100 biases. Now, hidden unit is going to act as an input to the output layer, right? Hidden unit responses. What are the responses we are going to get it after the activation function? Those responses are going to be connected to the output layer. How many output neurons I have? 26. So how many hidden units we have? 100. 100 into 26 is 2600 and 26 biases. So the total number of parameters for this simple architecture is 28K, right? So you may can ask a question that this is very simple and straightforward. We are trying to use a neural network for a image classification or image recognition problem. What are all the limitations of this particular existing conventional neural network architectures? The limitations here are, as you can able to see here, I hope you're able to see it here. Let's assume this is my input data. Try to focus on the location where there is a 2 green dots and 2 red dots are there, right? Try to focus on that. Now, what are we trying to do? What are the given input data is there? Simply you are converting into one-dimensional vector form. Simply you are using the flattening layer. With this particular flattened layer, you are passing to the neural network, right? So, can you please tell me one thing here? At that location, the location which I am highlighted here, at this location, there are 4 dots are there. So white is representing the pixel called 1, black is representing the pixel called 0 because it's a binary, right? So at that location, you are passing 1100, am I right? So as and when you are trying to pass on 1100, that means here the input neuron values are non-zeros you are passing. That means as and when you are trying to pass on to that particular neural network, there is a chance of getting a non-zero value at that location. But let's assume your given input data is a little bit translated towards the left side. Now at the same location, let's assume the same location, your input is little bit translated. That means the black character, whatever you are able to see it here, the number of pixels which are covered with the black are shifted towards the left side. Now in the same location, earlier you have passed 1100, now you are passing all zeros, right? Now, I hope you're clear. Earlier you have passed 1100, now you are passing all zeros. So as and when you are passing all zeros here, can you please tell me what could be the possible outcomes you can be able to get it at this location? As the all values are zeros are multiplying with any weights are become now zeros, right? So in the previous case, the output is possibility of non-zero, but in this case, the output value is 0. Now you tell me, the neural network architecture is remains same, but outputs are different. What was the reason for getting a 2 different outputs? Because input is sensitive to this translations, rotations, and scaling. So as you can be able to see it here, whenever you are trying to use such type of raw data with networks without doing any pre-processing on the given input sample. If you would like to restore it, there is a possibility of getting a distorted responses. I hope you're clear. So by using a simple conventional neural networks without uh, considering about the feature extraction part, you may going to end up with a generating a distorted responses. It means the conventional neural networks are sensitive to shifting, scaling, and other distortions. I hope you're clear on this particular point. Now, you may can ask a question that, okay, if it is a very sensitive to translation, scaling, and rotation, in the literature, how the others might be handle this issue? Because this is a general issue, right? As you can able to see it here, that directly you cannot able to use it. That means there should be some alternative ways to do that, right? Yeah. In order to solve such type of problem, there could be one possible solution with us right now is called convolutional neural networks. So convolutional neural networks is a concept which can also be called as a deep learning model. What is the meaning of a deep learning here? As you can able to see it here, this is my input, hidden layer 1, hidden layer 1, hidden layer 2, and so on. Hidden layer 2, and so on, output layer. So whenever you are using more than one hidden layer, what this particular architecture is called? If it is a neural network, this is called deep neural network. Because more than one hidden layer is involved here. It's the deep neural network. So whenever you're using a deep neural network, it is also called a deep learning. Because before getting an output, you're trying to analyzing the given input sample in a multiple levels, in multiple scales, you are analyzing it. Right? So this is also deep neural network. So what could be the difference of convolutional neural networks and the deep neural? Both are deep learning only, right? So there could be a little variation might be present, right? Yeah, there is a small variation that is called convolution. In the previous case of deep neural network and a convolutional neural network, the difference is here you are using a signal processing concept called convolution. What is the functionality of that? That we will going to see in a while. So here we are trying to use given input sample is passed into the multiple layers to get the desired output. This is a simple architecture of a CNN. We will go to see more in detail. Now you see it here, as I have asked it earlier, in the literature, how the others might be used deep neural networks or neural networks without handling the distortions. So you need to prevent the distortion, but also you need to use the capabilities of the neural networks or deep neural networks. What are the different ways to do it? So in order to do that, there is a strategy called feature extraction. What type of a feature extraction strategy you are going to be applied, proportionally, you are going to get the desired outputs. If your feature extractions are too good, that means your outputs also maybe the model learning can also be better, right? So in order to do that, there are different ways what there in the literature. As you can able to see, in this case, one data set. Here, the data set is the type of a data set is not important. So the one data set with the 6 class or 7 class problem, the number of classes are 6 or 7. The data division strategy that is called a training and testing is remains same, because you have to divide the data into training and testing. Machine learning model can be neural network here for your easy convenience, neural networks. But you can able to see the different results here. What could be the logic? Model is same. Sorry, the data set is same. Data division is also same. Machine learning is also same, but the results are vary. Why? The reason is, as you might be seeing this particular layer, input layer, whatever you are going to feed as an input to the input layer, this information plays a very significant role to make your model to understand. This entire model is going to be learned based on the whatever you are feeding. The information you're passing as an input is a good input, then obviously your model will try to understand better. To extract such meaningful information from the given raw data, these are all the different approaches which are presenting in the literature. This is called feature descriptors. So the way you are extracting the features are going to be designed by the users. Now you can ask a counter question. Sir, how to extract the features? Yeah, that could be the limitation, because as a human, we can think a finite number of ways to extract the information from the raw data, right? Maybe 10 different ways, 20 different ways only we may can try to think about it at a given point of time, right? Now, model accuracies are depending upon what type of the features you are extracting, and the features are extracted by users. But now with a given time, I need to get a more accuracy. Now my model has to perform better and it should be robust in nature. What to do now? In order to dependent upon the user, what are the features to be good for my given application? Now you are using a concept called convolutional neural networks, where with the help of the convolution, rather than extracting the features, you are learning the features. I hope you're clear, right? So you're trying to learning the features rather than extracting from the raw sample by a human, by using human intelligence. You are using your machine with the help of the convolutions. Your features are going to be extracted and the coefficients of the convolutions are going to be learned. So in a way, you're learning the features depending upon a given application. So if you might be seeing this entire pipeline from a given input raw sample, first you're applying the convolution operation. Then you are providing a non-linearity into it, that is with the help of some of the activation function. Again, you're repeating the process of convolution and activation. Then to reduce the spatial dimensionality, you're using the pooling operations. And you are repeating the same task, and at the end, you are using the fully connected. Now, as you can able to see fully connected, the term called fully connected is nothing but it is a simple neural network, right? So now you technically can see for this particular neural network, from where you are getting the input, you are getting the inputs after extracting some features with a sequential operations of the convolutions by using maybe pooling. Those features you are added as an input to the fully connected layers. I hope you could able to correlate the simple neural networks versus the CNN, right? But the only the difference in that and this here is that you are adding a convolution operation in between. Now let's go and see about the what is a convolution. So in a simplest form, the convolution is a mathematical operation between the two signals to generate the third one. The simplest form, okay? So here, how the convolutions are going to be performed. So here, let's assume a given input sample is RGB. The given input is 7x7 and you are using RGB channels here. So in order to perform a convolution, you are using a filter, doubly not filter, one filter with a 3x3 is my mask size. As my given input is RGB, to align with my depth, here we are using the 3x3x3. What are you trying to do now? You perform a convolution at this particular location, convolution in a way that perform a element-wise multiplication and the summation. You can perform the element-wise multiplication summation. So here the coefficients are there. It could be the random coefficients you can make and consider here. -1, -1, -1, 1, -1, 1, 0, -1, 0, -1, 1. So this is my one coefficients of a recursive convolution mask. Just you perform an element-wise multiplication here and sum it up. So for a one task, I will do it here, the given location. So here the element-wise multiplication summation is nothing but it is 1. It is 1 because everything is 0 and 1 is only one column is left out, right? Now let me do the same thing here. So whenever you are performing a convolution at this location, logically you can see these four portions are only non-zeros. So 2, 2, 2, 2. So multiply 2, 2, 2, 2. Here -2, -2, -4. Similarly, you apply here 1, 1, 2, 1, 1, 2, -1, -2, -3. Right? So what are the values here? 1, -4, that is called -3, -3 plus -3, -6, -6 plus bias 1 is -5. As you can able to see, -5. right? So this is what the element-wise multiplication and summation we are performing at a given location. Now, as you might be already studied about the convolutional part and what are all the other concepts which are involved here, while you, in order to perform the convolution response, that is called residual map, you can consider the outcomes of the convolutions are depending upon the what type of the padding you are applying and what type of the stride operations you are applying. Based on that, the resultant sizes are going to be dependent, right? Yeah. Now, second important factor is called pooling. So in the pooling, what is our main objective of the pooling? The pooling here is to reduce the spatial dimensionality by preserving the important features. So let's see, this is my image, raw image in RGB. As by looking up this particular image, this is a parrot is riding a cycle, right? So here you can able to see that once you are performing a convolution operation, you got the adjacent parrot. Now you are adjacent parrot. Now you are trying to reducing its scale by half. Now, even though you are trying to reducing the scale by half, now try to have a look. Here, the same parrot is riding a cycle, the structure is remains same, right? That has the advantage. It means while you are applying a pooling operation, you are trying to ensuring one thing that you need to reduce the number of pixels, but the important information need to be preserved because if the information got lost, model may not able to learn anything. So that is what the pooling will going to help us. Let's assume initial my image size is 100 cross 100. After convolution, whenever I'm performing a pooling operation, now I'm going to get the output of 50 cross 50. So 50 cross 50 means 2500 pixels are there as compared to that 100 cross 100, right? The less number of pixels are involved. And as and when you can apply the multiple pooling, the spatial dimensionalities are going to be get affected by trying to ensuring the required features. Now, let's assume this is a task where you may can able to think that what is the need of a convolution neural network architecture. So here you try to see it handwritten digit classification. So for this particular classification, what are all the different strategies you can able to apply to extract the features? So the different strategies are you may can go for the vertical lines, horizontal lines. So this is a horizontal line. Yeah. Vertical line, horizontal line, curves, semi-curves, circle, am I right? And diagonal lines and so on. Like this, you may can able to think some of the features you can able to extract so that wherever there will be a combination, maybe there could be a possibility of detecting the digit, right? But now you try to see it here. There is a way of representing 8. This is also an 8. But what are the features you have so far extracted? 1, 2, 3, 4, 5, 6 or 7 different features you have extracted. Those none of the features are going to be satisfying this digit called 8, right? Now, how you can able to make your model to understand this is a hand digit recognition? That is where the convolution part will come into the picture because here, as you can able to see it here, vertical line, horizontal lines, small circles, and so on. These are all the different features manually we are extracted and pass those features as input to the neural network in the conventional mechanism. Now, to avoid what type of features to be extracted, you are defining the number of convolutional masks. You are defining number of kernels. Based on that, your model is going to be learned. So in the same pipeline, if you can go for the different architectures, these are the popular convolutional architecture. This is called sequential architectures, right? So in the sequential architectures, if you can able to see, the given input is passed to the sequential convolution operation. Try to have a look into it. First apply convolution, pooling. Again convolution, pooling. Again convolution, convolution, pooling, and so on. That means sequentially one after other the operations are performed. Also try to observe here what type of the convolution mask sizes they have used, how many number of fully connected they have used. Here the fully connected they have used 3. Similarly for the VG16, they have used a fully connected 3. So LXNet and VG16, if you might be observed, both are sequential in nature, right? So both are sequential in nature. That means one after other the convolutions are happening, right? So now you try to observe the type of a mask size we are using. Here we are using the mask size of 3 cluster. That means uniform kernel size is applied across the architecture, and it is a deeper in nature. And number of channels they have used 64, 128, 256, 512, and so on. That means those many number of convolutional operators at a given layer they have applied, right? It is deeper in nature, and of course it is complex in nature, but it is a sequential in nature, right? Later on, they have in the ResNet one particular problem they have handled that is called loss of information. What is meant by loss of information? I'm going to show you in a while. So now there was a new part which they have introduced that is called a skip connection. We try to observe this particular skip connection here. What are we trying to do now? The initial information, first you perform some convolution, you got some output, right? That particular convolution outputs are you're re-adding after some repeated convolution operation. That means whenever you are performing a sequential operation one after other, there is a chance of loss of information. To prevent this particular loss of information, you are trying to add on its previous information to it at a given point of time. To add in this process, they have used a skip connection here. So ResNet is the one which is trying to adding the previous information so that the as and when the model go deeper, the information will be preserved. So I'm keep on using the term called information, right? I'm going to show you some pictorial variations in a while so that you will going to get a complete clarity. In the same year, the Google has introduced a new concept called modules. So that is called, they have introduced the inception module. What is the novelty of this inception module? This is an architecture which they have introduced the multi-layer, parallel layers, multi-scale filters. At a given location, you can use 1x1, 5x5, 3x3. Right? So you can ask a question, what is the need of these particular various scales? The answer is so simple. Let's assume you are trying to you applying on a face recognition problem. This is my face. This is my face. Let's assume once you are applying a 3x3, assume it is going to be covering this particular eyebrow part. We are applying a 5x5. Assume, right? So 5x5 is larger than the 3x3, right? What could be the difference? You can able to see it here. Whenever you are applying a 3x3 and eyebrow region, the 3x3 is going to fit into the eyebrow region, right? So within the eyebrow, everything is black. You are going to get the uniform information. But whereas you are applying a larger scale kernel at that particular location, there is a chance of getting the upper skin or the lower skin. That means you are going to get the edges to it. Am I right? So whenever you are applying the larger scale kernels, there is a possibility of getting the finite edges as well. So that could be the advantage of using the multi-scale filters. Just I'm going to show you in a while the visualization aspect, right? Now try to observe this. As I said, the sequential convolution operation, what are the limitations? So in the sequential convolution operation, try to observe here. This is my input. Perform some recursive convolution operation. First time, you got some result. You are repeating second time. Again, you are repeating third time. Now you tell me after third time, what are the points you have observed from this particular sample slide? Anybody can share your views? Let's assume, imagine you are trying to apply the same thing at the fourth time. What will going to happen? Are you going to get any meaningful information, or you're not going to get any meaningful information? In the fourth time, you can able to lose the information because the wrinkles part, as you can able to see, which is highlighted here. First time the wrinkles are highlighted, second time the wrinkles are polished, third time is more polished. In such a way, you are losing the information, right? And the fourth time, what are you going to get? In the fourth time, entire uniform information will be there. So what is the deep learning? The terminology called the deep learning, whenever we look in that, whenever you are applying the deeper architecture, you may going to get the better features. But here, if you can see it, as and when you are applying the deeper architecture, you are not going to get anything, right? So this is one observation which we need to apply, which we need to see before applying the algorithm. So second one is for your easy reference, like as you can able to see it here, from the given input sample, you have applied the three sequential operations. At the last, you can able to observe there is a information getting lost, right? How you can able to preserve some information as and when you go deeper. So AlexNet has introduced the skip connections. What is meant by skip connection? The first convoluted response, you can add it after the third one. Just you use the elementary summation. Now you see, as and when you're doing the element-wise summation, this is the response. So here the faces and the outliers are going to be highlighted, right? So this is what the skip connection is going to be, a residual connection. We are going to get a more detailed information. I hope this is clear to you. Now, again, second question may come here is that, what are the advantages of using the parallel architectures? First one is sequential in nature, right? Like Google has given an inception model where the parallelization they have introduced, right? So in the parallelization, what are the advantages? Here, sequentially, you are applying the 3 convolution operations, right? But here I'm trying to do the 2 convolution operations in parallel and summing up. So now you see the pictorial visualization of the results after parallelization and sequential. So in the parallelization, what are you trying to do? You are trying to pass on more detailed information to the next layers. That means the as and when you are passing a more meaningful information, your model could able to understand much better, right? So now how many layers you are using? With the minimum number of layers, you are able to get it. So this is another advantage of the parallel architecture. So you can ask one more question here, as I highlighted earlier. Do we require to use a uniform scale filters? Answer is no, not required. You can also use a multi-scale filters, as you can able to see 3 cross 3 and 5 cross 5. So whenever you're using the various scale filters, now you can able to see the outcome. As you're applying, as you can able to see the uniform scale filters, here the using the multi-scale filter, the resultant outputs are completely different and highlighting the more edges, right? This is the advantage of the using the multi-scale filter. Now you can think that in which scenario I need to use uniform or multi-scale filter. Logic is so simple. Whenever your data is having a variable scale objects, your size of the objects are varying. In such scenario, using these multi-scale filters are more advantageous. Now, rather than discussing more existing architectures, let's assume you have VG16, ResNet, GoogleNet, Inception model. These are all have trained on the imaginary dataset. This is one of the very popular dataset and complex dataset, right? So in order to train such type of a large, deep architecture, we need an infrastructure, right? But now let's assume in our case, we do not have the high end infrastructure. Now, how you can able to transfer the knowledge from X to Y? In order to do that, we have a concept in the literature that's called transfer learning, right? So what are we trying to do? So let me directly go to the part. You will be able to understand. Let's assume initially I have trained my model on the detection of the circles, triangle, and so on, right? Now your objective here is to, as the existing model are able to detect the shapes. Now, what are we trying to do? Using this particular knowledge, you can take the circles and the triangle, use the knowledge, and you can able to retrain it for the another shape. I hope you're clear now. So this was the advantage of the transfer learning. You're trying to transferring knowledge from one to other, because your model also know what are the diagonal lines, what are the corner points, what is a circle. This model already has the knowledge on earlier because it is already trained earlier individually. Now what I'm trying to do, I am using this existing knowledge and I am trying to using this knowledge for predicting or detecting the new task. So you can use this transfer learning in 3 different ways, because in the literature we have 3 different ways of transfer learning concepts are there. One is inductive, transductive, and unsupervised. What is meant by inductive? Inductive is nothing but where the model, whatever you are trying to picking up, that particular model is trained on the supervised data, right? So, and the same model you are using for the new label data. That means one classification problem where the labels are exist, or whatever the application, the model which is already having a labels to it, you are using for the another, you are transferring the knowledge from supervised to supervised. That is called inductive. Now, transductive nothing but the model you are picking is from the trained and the supervised, but now you are trying to pass on that knowledge or transfer that knowledge to unsupervised dataset. This process is called transductive. That means your model X is trained VG16, for example. For a sake, VG16 is used for the used on the imaginary dataset discovery classification problem, but the architecture capabilities you are trying to pass on to the some restoration task. So the restoration, that means output size is as equivalent to the input size. So if that is a cases, maybe you can use the transductive. Unsupervised means, of course, yes, the model got trained on the unsupervised data, and you're transferring the knowledge to the unsupervised data as well. Now, how you can able to do this transfer learning? There are two different ways are there. Either you can do the bottom layers you can able to handle it, or the top layers you can able to handle it. So either in the one of the layer you can able to use as a knowledge transfer. Let's see how it can be. Now let's assume I have a task here. Let's assume this is my VG16. For your easy reference I'm talking about, okay? This is my VG16. I have used it for the imaginary data set with 1000 classes are there, okay? Now what I'm trying to do now, in this particular VG16, initial layers, or rather initial 2-3 layers are there. As this is got trained on the complex data, I am trying to use those 2-layer features as these and defining the new convolution operations depending upon my requirement for the cat and dog classes. For example, I am trying to use the cat and dog, assume. Okay. So ImageNet is having 1,000 different classes. It is the VG16 have a diverse nature. It already trained on diverse data sets, so the model could able to model has having a very diverse knowledge it is having. Now, what are you trying to do? Initial 2 layers, you are going to use it. That is called you are going to frozen, as you can able to see the log symbol here. Initial as it is 2 layers you are using, and the rest of the new layers, depending upon your task, you are defining it, and you are only training those layers only. This is a one way of transfer learning, right? So let's assume initial 2 layers have frozen, and rest of the layers got trained. What are the advantages of it? Your model can able to learn quickly because the initial 2 layers played a very important role, right? There is another approach is called bottom up approach. No, initial 2 layers I do not want to maintain, but last layer fully connected, or I am going to use a 2 fully connected. So last 2 layers I can use it. Now I want your answer. Rather than using initial 2 layers, can we use the last two layers here? Can we do that? Then from the scratch, can we train the rest of the layers for the task B? Just you can think and you can give me an answer. If your answer is yes, give me the reason. If the answer is no, again try to give me the reason. Okay. Now let's assume initially you might be frozen the weights, but later on you are going to, if you wish to make your model to be suits to the task B, you can fine tune as well. Fine tuning is nothing but initially those weights have learned. Later on, these frozen weights can be unfrozen, so that model can able to understand the features much better. How many of you are not able to understand my question? Please tell me. If you could not able to understand my question, I will repeat it again. Okay, for your quick reference, let me repeat that. Here, initial 2 layers, we are picking from the previous architecture, that's from the task here, right? My question is, I do not want to use the initial 2 layers, but I want to use the last 2 layers. Clear? So here, those last 2 layers, I will keep it here. Here, I will use the last 2 layers. Rest of these all layers, I'm going to train it. This is also can be done, right? This is also one type of transfer learning. But which one will be more effective? And what could be the logic? That's what my question is, right? You may can think about it and share your answer till I'll complete the topic, okay? So, as I said, there are 2 different ways we can able to train your model. First one is that pre-trained model, you can use it the initial weights, and rest of the models you can able to train it by applying this frozen part. But later on, I'm trying to update the pre-trained model weights also. This is called fine tuning, right? So let's assume you have developed a very tiny model. That tiny model can be you are developing a tiny model for a given application, like maybe cat and dog. So you may can think that the initial model could be having a diverse knowledge. Sometimes the diverse knowledge may be not required for you. Initially, it might be required. Later on, to completely develop a customized solution, you may go for the fine tuning. As and when you go for the fine tuning, your model can able to memorize the um, application specific task. It will work. That is the advantage of using the fine tuning. Now we can have a common question that when and where we can use this particular no, what type of a transfer learning we can use, in what scenario you can use. Let's assume you have a very large data set you have, and your model got trained on a large data set that is called model A. For the model B, you're trying to apply on the completely different data set. For example, model A is working on the natural data set, but model B is trying to working on the medical data set. Like both might be for a classification, right? Right? So both are two different nature. What to do now? Option number one, model B can be trained from the scratch. You can design your model for the medical data and you can do it. Otherwise, pick the initial 1 or 2 layers from the model A, do the training. Let's see. Second one is, you have trained your model on the very large data set, but you are trying task B is also in the similar data set because there is no much variation. So now what you can do, simply you can do the fine tuning because the model A is already having a sufficient amount of knowledge and understanding the data, right? So in such scenarios, model B just you can go for the fine tuning. Simple. Yeah, somebody has answered. Sir, using the last 2 layers will be more effective because using the back propagation, we can make the new information reach to the initial layers, but using the initial layer back propagation not help. I think you should rethink about it. Okay, maybe if anybody wants to counter, maybe you can. Anybody can defend or anybody can oppose. Have understand. No problem. I'll go to give the answer in a while. Let's say the model A got trained on a very small data set. Now you're trying to, model B is trying to train on a very different data set. Here the number of samples are very smaller in nature, right? So two distinct data applications with the small number of samples are there, right? Now using the earlier layers may be somewhat useful because of course the model is very smaller in nature. So data is very small in nature. Initially you can use the initial layers and just you can use it. Let's assume you're trying to do on the same data set, similar type of data set, but both are in smaller. Better you can train from the scratch. That could be the better solution. So these are some of the papers where I'm going to share the slides so you guys can have a look into it. Okay. These are some of the slides where we can see the transfer learning for the different applications like hyperspectral and all. Now you see it here. The imaginary data set is there. It is for the cat, dog, ball, and so on. But for the hyperspectral, there is no direct relation. But some of the layers from the ImageNet for the VG16, for example, can be used as it is here, Then some few layers can be defined and we can fine tune it for the hyperspectral imaging. This is what I'm talking about, the transfer learning. Now let's coming to the question which I have raised. Whenever you are going to freezing the initial layers, the information whatever you are going to get in the beginning will be more effective. So as you can able to see it here, once you are performing a initial layers, the high level edge informations already the model weights have already properly learned. That means the convolution mask coefficients are very well better features it can able to give it to you, right? So as and when you are getting a very good features, the rest of the convolution masks can be learned very quickly. But whereas you are trying to freeze the last layers, last layer won't help. Last layers mostly not going to help us much because if the initial layers are not good, if those all values are trying to be uniform in nature, uniform is in the same values are there. So as and when we are passing a similar values to the fully connected, it won't able to make any much variations. But whereas if you are trying to use the freezing the initial layers where you can able to get the better features, then your model can able to converge much faster and better. So that is the reason maybe we try to prefer the initial layers selection rather than the bottom layers. I hope somewhat you're clear. So these are all some of the literatures for this particular transfer learning part. If you're interested, you can go through it. So as we have a limited time, just I'll take a minute and I'll pause for taking the questions here. So what are the neural networks we have discussed? You can just continue or extending the neural networks with a sequential model. Just I'll give you the very simple thing and I'll stop it in a while. Now let's assume this is my static data. Can you please tell me in which direction this ball is rolling? Can we say in which direction it is rolling? Answer is no. We can't say because it can go in any infinite directions. It can go to any direction, right? But what if I can give you its previous instances to it? At a given time, this is the ball position, but I know its previous instances as well. Now, can you please tell me in which direction the ball can roll now? So here you can able to see that considering about the directions, we can say that it can go towards the right side. Am I right? It means that if I am able to provide you the information which is varying with respect to time, then there is a possibility for you to predict or detect, right? That means you are trying to analyzing something on the time series data. That is what sequential modeling I'm talking about. Now have a look into it. Can you please tell me by looking up this particular image what this image is? Because it's static in nature, right? What is this image? Can anybody can share what is this? Maybe this is a school, play school, maybe, right? So yeah, this could be the kindergarten classroom. So how this model can able to understand the kindergarten classroom or the play school? Just it is trying to observe in the various objects which are presenting in the given input image. So there is a TV, there is a chairs, there is a kid, right? So depending upon the different objects, whatever it is able to understand, TV, person, chair, and so on, it is saying that, okay, this could be the kindergarten class, right? Now you may can ask a questioning answering also. What color is the chair is? There are two chairs are there. The one chair is getting dominating. That is called the color of the chair is in red in nature. Am I right? So you can pass an image as a query, pass a query in a form of a text, but you can able to get the answer again in a form of a text by analyzing an image. Am I right? Is there a questioning answering? So now you see, I want you to see this. Can you please tell me what will the girl do next? Because as so far you have analyzed something on the sequential modeling. Sorry, as you have analyzed in the um, static data. But now I have asked a question, what will the girl do next? Now the question is having some action into it. Try to have a look into this. Can you tell me what the girl will do? Pick up the chair. See, right? So as in when you are able to see whenever the question is having an action is involved, now if you would like to conclude that the girl remove the chair, right? Or it can be pick up the chair, right? So as and when it is whether the girl is going to pick up the chair, what could be the action as you can able to see here? Baby got fall down. Now the thing is how you can able to come to that conclusion. By showing a one frame, you may not able to come to that conclusion, right? That means you need a analysis between the frames which is varying with respect to time. That is called sequential data analytics or time series data analysis. So I hope you are able to understand. So how you can do that? Process is so simple. What are the things we have discussed in the earlier, that is on the neural networks, right? What we are trying to do in the neural networks? I have at a given instant I have inputs passing to some hidden layers to get the desired output for that particular instance. Am I right? What I will do, let me repeat the same neural networks for each and every interval. As let's assume the video is having a 30 frames per second. For a given 1 second, I have some 30 frames are there. Let me repeat this particular neural networks part 30 number of times. Now, can we say, as and when you are for each and every instance you are applying the neural networks, can we say this is a sequential model? Of course, yes, you are going to get the outputs for each and every instance, but can you say this is a sequential model? Okay, answer is no. Why? Why we can't say it is a sequential model? Because every instance you are getting an output. But the problem is, you are not making a relation between the instances. If the conclusions are based on the relation between the frames, then it can be called as sequential data processing, right? So this, if you can able to make a relation between the instances, then it can be called recurrent neural network. In the previous case, it is a neural network. Now you are repeating the same task again and again and again. This is called a recurrent neural networks by making a relation between the hidden states. This is the unfolded version. This is the folded version. So there is a recurrent loop. I hope you're clear. So there are many, of course, slides are there, but in consideration of the time limits, I'm stopping here. If anybody having any questions, you are feel free to ask me. Just as I'm going to share the slide, just I'm going to show you some of the slides here. But meanwhile, you can post your questions, whatever you have. Yeah. Anybody having any questions, please feel free to ask. The same thing, whatever we have discussed, just I want to extend it to the next level. Could you please show the last part along? Okay. So in the last part, in the last part, what we have done here, for every instance, we are repeating the neural networks part, but you have not considered the relation between the hidden states. You have not considered. So if you can able to make a relation between the hidden states as well, then it is called recurrent neural networks. This is a unfolded version because it is spreaded, right, for each and every instance. But the same thing can be shown here. This is called a folded version. Yeah, somebody is asking, while going down the layer, filter size should be decreased or increased. It's purely depending upon the here the filter size of the filter is purely depending upon your architectural design. Whether it can be, you can maintain a uniform filter like a VG16, you can maintain a uniform filter. Or if you want to use a variable scale filter, that is again you can decide. But the number of channels you're supposed to be going to be get affected as and when you go deeper. To process a video temporarily, for example, can we use any other algorithm than sequential modeling or attention? Yeah, for video analytics, we are going to use a 3D CNN, right? Because recurrent neural networks are there. These are all the very popular for the text processing in olden days. Then CNN came, then CNN 3D convolutions are there. Now transformers are there, then vision transformers are there. Now you know that sequential modeling, we are using these LLMs and different variants, right? Yeah, any more questions, please?
I think there are no other questions. Yeah, any queries from the participant side?
Any more questions, please? Just I'm trying to open the chart again.
So there's one question regarding semantic segmentation versus instance-based segmentation.
Okay. semantic versus instance segmentation. See, let's assume you have in an image there will be 4 to 5 images are there, right? So for each and every image, if you're trying to make a segmentation, it could be based on the instances. How many instances are there? But if rather than going for that, you are only looking for the cat or looking for the dog, depending upon your requirement. That is for semantic segmentation. Any other?
No. Oh,
Fine.
no, sir. There are no other questions.
Okay.
Yeah.
Thank
Thank you.
you, Deepak, for the
Thank
time.
you. Thank you
This is
so
a
much,
1 hour.
sir. Yeah. I
Uh,
completely understand within an hour. But sir, you
so
have managed it really well, sir. You have explained everything, starting from the convolution, the operations. Even sir has also discussed about different popular CNN architectures and how to use those architectures, especially using transfer learning, right, which are very, very useful. So also sir has talked, at least given some hints regarding the models, like especially recurrent neural network and all, why there is a need of recurrent neural network. You can explore more about it later on, but sir has already shown why there is a need of this, right? So with a beautiful example, at least, where you have only predicted what is the need of this kind of architectures. So thank you so much, sir, for your wonderful lecture, for sparing time with us.
thank you, Deepak. Thank you once again for the AICT Academy. Looking
Thank
forward
you,
to
sir.
meet you.
Thank
Thank
you
you, man.
so much.
I'll share the slide in a while.
Sure, sir. Sure, sir. Thank you, sir. Thank you, sir. So participants